All right, so before we move on, I do want to take maybe today, tomorrow, to talk about some of the applications of exponentials before we move on to the next topic. Partially because there's a exponential form that we didn't really discuss, okay? And that's over here. So particularly today, we're going to talk about compound interest. Now this, I mentioned this yesterday, I think. Compound interest is applied to a few different things. One of them is this: if you take a bank loan, okay, you are charged interest. You know, if you borrow $100, you owe the bank $120. Okay, you're paying for borrowing their money. That's compound interest. You also earn interest if you have a savings account. So if you put $100 into a bank, depending on the percentage, you get money back. You know, after a month or two, you may have $110 or something like that. But one part of this form, okay, is this number on the outside. So we haven't seen that yet. And I wanted to bring this up because there are quite a few very simple mistakes that are made with this that we have to be careful with. Looking at this form over here, okay, if you have to calculate something like 2 times 5 squared, we have to follow our order of operations. All right, parentheses and exponents come first. Do not, I cannot emphasize this enough, do not multiply 2 times 5 and then square that. All right, you're going to do 5 squared first, which would be 25, and then multiply that by 2 to get 50. All right. Otherwise, you know, if you don't follow order of operations, 2 times 5 is 10. 10 squared is 100. All right, so that's way off of what you're supposed to get. So tonight you're going to have some short homework where you're just calculating. All right, so you're going to have some stuff like this. So here, going back to compound interest, there's a few parts here. All right, we got a few different variables. Now, usually you're given all this stuff and you just have to find this. So here we have P is called the principal, which means your starting amount of money. So how much either you borrow or how much money you deposit into the savings account. So it's your initial starting point, okay? The R is the interest rate, okay, which is a percentage. So if you're given a problem like this, just be careful. If you're given, 20%, you're not going to plug 20 in here. Remember, 20% is going to be 0.2, right? We divide our percentages by 100 to get the decimal value. N is very specific to this problem because it's the number of times compounded. What that means is, so let's say I'm borrowing money. So depending on what plan I use, or however I borrow the money, they add on interest in different ways, okay? And that's called compounded. So they compound it, and when they compound it, that's when they add the interest on. So sometimes they compound it yearly, which means that once a year the interest gets added on. So if you originally borrowed $100, and whatever percentage they get, say you're adding $10, well, that you won't see that extra $10 until the end of the year, right? Sometimes they compound it shorter. They might compound it monthly, right? So at the end of every month, that interest gets added on. Sometimes they compound it weekly, right? So at the end of every week. So what happens? Oh, and then the T is just time, right? So how long it's in there for, and that's usually in years. So this is one way to calculate interest, okay? But something happens when we increase the n. All right. If I'm increasing how many times it's compounded, all of our values kind of tend to go in one direction. So the largest compound that we can have is daily, right? So every day interest is added on to your what you owe. And it kind of, it's not entirely favorable if you're borrowing money. It's something that you want if you are saving money. So the way it works is, all right, so say again, I'm just picking easy numbers here. How do I, yeah, I'll borrow $100. Okay. So say it's, 2% interest rate. So I multiply 100 by 2%, and that's $2, right? So that means $2 gets added on at the end of the day. So if I didn't pay off that $100 back, if I don't pay off the loan, then the interest adds to it. So the second day, instead of owing $100, now I owe $102. The third day, I'm taking another 2%, but it's not on the original $100. It's on what's in what I owe right now. So the 102. So it scales a little quicker than just, multiplying it by 0.02 and adding that on every time, right? So, I mean, if we're talking about 2%, it's not much, right? So if we have 100, the next day would be 102, right? And then the next day would be like 104.2, and then the next day, right? So it keeps adding on depending on what it was before, right? And that would be the daily. So, I mean, that works anyway. So if it's monthly, it's not getting added on as quickly. But when we do it more often, okay, we call that continuously compounded. And this part here, as it doesn't really matter what the rate is, but as that n gets larger and larger, this part here mathematically goes towards our natural exponential function. So continuously compound interest, there's a different function. We still have the p, e to the rt. All right, so we're going to take a look at a few examples with this. All right, just calculating it. So all right, so let's look at an example. So we're going to invest, right? So again, this can be applied both ways, and it's the same process, right? If you're borrowing money or if you're investing money. So we're investing $12,000 at a rate of 3%. We want to find the balance if it is continuously compounded for 5 years. All right, so I didn't mention this before, but A is how much money you have in the account or how much money you owe total, right, after everything. So with problems like these, I like to write everything down that I know, all right, and then what we're trying to figure out. So we're trying to figure out our final bank account amount, okay, A for amount, we'll say. The principal, what we start with, okay, is the 12,000. Excuse me. My rate is 3%, which we can't use the percentage, so as a decimal, that's 0.03. And then my time is 5 years. All right, so we're going to plug this in. A equals 12,000 times E Now, R, again, was 0.03 times 5. All right? So with this, okay, we're going to do this in a few steps. The first thing we're going to do is we're going to simplify this exponent. All right? So we're going to do 0.03 times 5. Let me get 0.15. All right, so I'm going to have, write it over here. (12,000e to the 0.15). Now this next step depends on how you're calculating it, right? What, if you're using a calculator, if you're doing something online, or if you're using your phone. If you are using your phone, you have to do this part first. Okay, so again, real quick, I'll show you. So again, my calculator is a little different because I already have the E here, right? You might have to turn it into landscape mode. When you get landscape mode, you get, all the trig functions, sine, cosine, all that. You have the pi. Again, there's E, right? So I would do E. This one, it doesn't have the exponent there, so I'd have to do the, oh, not that. How do I? Okay, I would hit that little caret button to give me the exponent. And then 0.15. All right, and that's equal to, all right, so you're going to get, with E, you're going to get a crazy decimal. Don't bother trying to write it down, right? I mean, it goes on forever. I'm not, What happens, though, is if you round it, you're changing the problem, right? You're changing the actual amount. So I'll show you in a second. So with this, for your phone, if you just want to use this number, right? Because all I want to do now is take this value and multiply it by 12,000. So I just have to, oops. I keep this there, and I just hit times, right? And that automatically takes everything that it had before, times 12,000. So after 5 years, your $12,000 becomes 13,942. Almost, yeah, almost even there, 13,942. So after 5 years, you get $1,000, almost $2,000. So let's see real quick if we calculate it a little differently. So I'm going to do, again, e to the 0.01, nope, 0.15, nope. So let's say I just do 1.16. I deleted it there. So I rounded it to 1.16. So I do 1,200 times 1.16. Okay, that's a lot. I mean, it's not a lot less, but it is less than the answer that we had before. All right. So with problems like this, you want to be as accurate as possible. And the only way you can be as accurate as possible is to use as many decimals as possible. Okay. That's if you use your phone. If you're using an online program or a actual graphing calculator, it's a little nicer because you can just type everything in at once. All right. So if you have one of these, all right, you have this. Let's see if I can. No, the focus is terrible. Here we have e to the x. So you hit the second button and that, right? And it puts the e there, and it automatically puts the exponent there. And we're going to just type in that 0.15. And there we go. That's everything that we had there. Right. So before it was 13,920 when I did it the other way, right? So we'd be losing out $22 if I did it with rounding. Right? Any questions about that? All right. So another application that we can use exponential functions with is in science something called radioactive decay. Are you good? I'm sorry, you guys took chemistry already?
Yeah.
Okay. So, did you guys learn about half-life?
No.
Okay. All right. So, quick lesson. So, anytime you have a radioactive substance, or actually most substances, did you guys learn about carbon dating?
Yeah.
Oh,
Okay. Do those words look familiar?
Nope.
All right. So, quick science lesson. Every living thing on Earth is made up of carbon. Okay, we have carbon in it. All life forms are carbon based. Okay, carbon is one of the basic elements. I mean, it's, by itself, carbon is coal and diamonds. All right. Don't get me started about diamonds. They're really useless. It's all marketing and capitalism. Don't buy diamonds. It's literally just coal. Eventually, they'll turn to dust. But everything is made out of carbon, right? A specific type of carbon. Is it here? No. I think it's like carbon-16. So what they do is, they find a fossil and they measure how much carbon is in it. By measuring how much carbon is in it, they can go back and they can tell how old that fossil is, right? And that's based on something called half-life. So any radioactive element or any element eventually decays. All right, conservation of energy. It's constantly using energy. The atoms are moving around. So, sometimes it takes thousands of years. Okay, carbon, I think it has a half-life of about 5,000 years. So if you had a gram of carbon, in 5,000 years, it would be half a gram of carbon. In another 5,000 years, it would be half of that, so a quarter gram of carbon. Right? And essentially, that's how they use carbon dating. Now, different elements have different half-lives. Something that's more radioactive, like uranium or plutonium, where they use in nuclear reactors, that has a carbon life of, sometimes days or hours, right? So you start with a gram of plutonium, by the end of the month, it's almost gone, or, whatever. I'm just, picking random elements. So, that's a lot to write. I don't want to write all that. So for this particular example, we're going to be talking about Chernobyl. All right. Are you guys familiar with Chernobyl? If you watched the HBO show or learned about it in history, it's a Russian nuclear plant that had a meltdown. So everything, all the nuclear waste and all the nuclear products leaked, and they had to put a giant dome over it. It was a huge catastrophe. So that had plutonium in it. So plutonium is actually particularly dangerous because it has such a large half-life. Its half-life is over 24,000 years, right? So that's why, people are worried about nuclear waste. You bury something like plutonium, that's going to be there long after we're dead, right? And all the time, it's actually polluting. It's sending radioactive waste, radioactive waves out. So usually they bury it miles under the ground, all right? At least they try to. So with half-life, okay, we actually have our base is 1/2. So remember, when our base is 1/2, that's technically a negative exponent when we have a fraction. So our graph is going to look something like this, right? Maybe not this far over. It might be, a little more this way, actually, right? So something like that. So you can tell how much we start with, Okay, just like before, usually this number out in the front is our starting amount. All right, so here we're starting with, say 10 grams of plutonium. Right, the plutonium has a half-life of 24,000 years. Oh, actually, that's okay. Yeah, whatever. So we want to find out how much is left after 100,000 years. All right, so say there's an accident, somebody dropped some plutonium, 10 grams of plutonium, and it's just sitting there. Nobody touches it. Maybe it's in the middle of the ocean. We want to find out how much longer it's going to last for. All right, so with something like this, all right, we're just plugging in and evaluating. So I'm going to have 10 times 1/2 to the 100,000 over 24,100. All right, so just to break it down, doing the exponent first, right? If I have 100,000 to one more by 24,100, okay, this number would be your new exponent, okay? Now, again, if you have one of these calculators, you can literally type all this in at once, right? But I'm going to do it step by step. So now I'm going to raise 1/2 or 0.5. Now, again, I want to be as accurate as possible, but there's no way I'm going to write down all these decimals, and it's going to keep going on forever, right? Or maybe not forever, but it's going to go on for a while. So I'm raising it. No, that's not the button I wanted. So I'm raising it to a power. Now, I want to be, again, as accurate as possible, so I just want to plug this answer in. So on some of your calculators, you're going to see ANS, right? So I'm going to hit second and ANS. That ANS takes your previous answer in its entirety and plugs it in. All right, so I do that. We get 0.05, right? So that's the factor that it's changing by, so I'm going to multiply that by 10. Wait a second. What'd I do wrong? That's not right. Oh, no. Okay, yeah. So after 100,000 years, we still have 0.5 grams of plutonium, which, again, it's still giving off radioactive decay, and it's still polluting things. Okay, so that was a nice little quick science lesson and financial lesson. All right, so I'm going to give you a couple word problems tonight that are pretty much directly tied with this. All right, there'll probably be one with interest or whatever, and one with radioactive decay. I'll give you the equation for radioactive decay, but just remember that the interest one that you're going to be using, okay, is the one I gave you before. Okay, A equals P times E to the RT. All right, and then after that, tomorrow we'll look at some new stuff. We'll move on. All right, guys. So yeah, keep an eye out for that homework. That'll probably go up in a little bit. We'll go over that tomorrow and move to logarithms, which should be completely new. So we'll have some fun there.